Welcome to the deep dive. Today we're looking at something maybe a bit overlooked in space exploration: calibration.
Absolutely. It's fundamental.
Yeah, it underpins, well, basically every discovery our space telescopes make. But there's a huge catch, right? A tiny drift, maybe a subtle bias creeps into the data, and poof, your big finding. It might just be an artifact. Bad calibration.
It can completely mislead scientists. You think you've found something profound, but it's just noise, essentially. That undermines the whole effort.
Which is exactly why NASA's ArcStone mission is so interesting. It's a tiny CubeSat, a 6U, so what, shoebox size?
Roughly, yeah. Packed pretty densely, though.
And it has this really ambitious goal, like use the moon to totally change how we calibrate instruments up there.
Okay, let's unpack that. The moon. How does that work?
Well, think about it. The problem is massive because without a consistent, unchanging reference point.
Like a cosmic yardstick.
Exactly. A yardstick that doesn't stretch or shrink. Without that, the data we get back is just riddled with uncertainty. Makes trusting the findings incredibly difficult. And the ways we do it now, they have drawbacks. Ground telescopes, well, they're looking through our messy atmosphere.
Right. Clouds, dust, turbulence. It's like trying to see fine detail through rippling water. Just adds noise.
Loads of noise. And even space missions, they often have onboard calibration tools.
They do, but those tools themselves can degrade. Like an old light bulb dimming over time, they lose their known brightness, their stability.
So the standard isn't standard anymore.
Precisely. And that affects the accuracy.
So the moon, why is it the answer?
This is the brilliant part. What's fascinating here is the moon's surface. It's incredibly stable, geologically dead, mostly unchanging over human timescales.
Okay.
And its reflectivity, what scientists call albedo, is remarkably consistent. It doesn't really change much.
So it's a reliable, steady source of light.
Exactly, a stable benchmark. And crucially, ArcStone looks at the moon from space, outside Earth's atmosphere.
So no atmospheric interference. Clean signal.
Clean signal, pristine view, no clouds, no aerosols getting in the way.
Okay, that makes sense. But let's dive into ArcStone itself. It just launched, right? Recently.
Very recently, June 23rd, 2025, from Vandenberg on a SpaceX rideshare.
And it's getting set up now.
Yep, it's in its 3-week commissioning phase, just checking everything out. Then it starts a 6-month campaign collecting data, really trying to nail down this lunar calibration idea.
6 months of staring at the moon, basically. What's packed into that little box to let it do that?
It's got some impressive tech. The core is a precision spectrograph from Resonon. That's the instrument measuring the moonlight's color spectrum in detail.
Okay.
That's integrated into the CubeSat bus, the main body and systems provided by Blue Canyon Technologies. They also handle the guidance and navigation.
And the pointing has to be good, I imagine.
Absolutely critical. It has sub-arcsecond pointing accuracy. That means it can aim so precisely.
Like pinpoint precision.
Yeah, it can repeatedly target the exact same small patch of lunar surface over and over. That consistency is key for mapping the moon's reflectance accurately across different illumination angles.
Okay, incredible precision. But how do we, trust ArcStone itself? How do we know its measurements are right? What's the validation plan?
Good question. It's a rigorous process. ArcStone won't just take one snapshot. It'll observe the moon through multiple phases, different sun angles.
Mapping the brightness across different wavelengths.
Exactly. Building a detailed map. Then, crucially, they compare ArcStone's space-based readings with existing data from ground telescopes and other orbital assets.
Cross-referencing.
Right. By comparing them, scientists can isolate and quantify those atmospheric effects that plague ground observations and any remaining instrumental quirks or offsets. It lets them build up confidence in the lunar model.
So it sort of calibrates the calibration method itself, in a way.
That's a good way to put it. It establishes the moon as a reliable standard by carefully accounting for all the variables.
It really is quite something. A shoebox-sized satellite potentially fixing a decades-old problem in astrophysics and earth science. What are the sort of bigger picture implications if this works?
Oh, the potential is genuinely transformative. If ArcStone is successful, it could firmly establish the moon as the primary calibration standard for space-based observation.
A universal standard.
A universal, stable, reliable standard. Think about it, we might even be able to go back and correct old data sets, data collected over decades.
Wow, removing biases from historical observations.
Potentially, yes. Imagine refining our understanding based on cleaner historical data. And looking forward, A follow-on mission could institutionalize this, make lunar calibration routine.
So different satellites could calibrate against the moon in real time.
Exactly. Cross-calibrating different platforms, Earth
Right.
observation satellites, telescopes looking out into the cosmos. This could massively boost the accuracy of Earth science, for instance.
Like for climate change studies.
Absolutely. Detecting those very subtle, long-term climate signals requires incredibly stable, reliable measurements. Better calibration means higher confidence in those critical findings.
It's amazing. Such a small mission, Arkstone, but with a potentially huge impact on how we understand our planet and, well, everything else out there.
It really is. And, this raises an interesting question, maybe for you listening. What else might we learn? What sort of secondary science could pop out from 6 months of staring at the moon with such a precise spectrograph? Or how might Arkstone's results actually change how we design the next generation of instruments?
Yeah.
We don't know yet.
Yeah.
The scientific community, like you, is definitely eager to find out.